First of all, annuities. Now, the previous situations that we've talked about in sections 1 and 2 mostly involved what's called a lump sum payment, which means that you put all of the money into the account up front and then allow it to accumulate interest and don't touch it. But many situations involve a sequence of payments that are made at regular intervals. For example, a mortgage on your house, you're going to make monthly payments on that. You're going to make monthly payments on a car loan. Even retirement benefits are usually monthly payments. An annuity is a sequence of equal payments that are made at regular, equal periods of time. So all of these can actually be looked at as annuities. A couple terms. First of all, the payment period is the time between payments. The term refers to the time from the beginning of the first payment period to the end of the last. Annuities can be used to build funds like savings accounts and retirement accounts, and they can also be used to pay out funds like when you retire, they pay out your retirement benefits. Also, lottery and sweepstake winnings are often paid out over time. Okay, a little math fact here. If x is a real number and n is a positive integer, then 1 plus x squared plus x to the third, all the way up to x to the n minus 1, can be figured out using this little formula, x to the n minus 1 over x minus 1. And if you're wondering why there's a 1 up front, if you look at the powers of x, think of the 1 being x to the 0. So what you really have here are powers of x that you're adding up from 0 to 1 less than your end goal. And we're going to use this fact in some of our formulas. You can even try this on your calculator and show that it actually works. Okay, we're going to use an example to kind of build our formula. We're going to look at how it works. And then we'll get the formula and you'll use that for the rest of the problems. Let's say you're depositing $1,500 at the end of each year for 6 years. The account pays 8% interest and it's compounded annually. You need to find the future value of this account. All right, let's look at a picture of this. The term of the annuity is 6 years, and you are paying into the account $1,500 at the end of each year. So you can see how that works there. Okay, so this is what it's going to look like when we factor in the compounded interest. The first year you deposit $1,500, and that $1,500 is going to accumulate interest over the next 5 years. So that particular $1,500 at the end of the term is going to be worth 1,500 times 1.08 to the 5th power, because it was 5 years where it was accumulating the 8% interest. What you put in at the end of year 2 is going to sit in there for 4 years. So the interest and principal on that is 1,500 times 1.08 to the 4th. And then you can see year 3, year 2, year 4, year 5, and then finally year 6, you're putting in $1,500 at the end of the year. It accumulates nothing, and it's just the $1,500. So we have the principal all the way down for each payment, and then you'll notice we have that 1.08. For year 6, you can think of it as 1.08 to the 0 power. For year 5, 1.08 to the 1st. For 4, 1.08 to the 2nd on down. In fact, we go from 0 to 5, which is 1 less than the 6 years. And that's how it relates back to that math fact that we mentioned at the beginning. So we're going to use that math fact to calculate the amount of money here. So it's $1,500 because that's how much you're depositing each month, and then we're using our little formula, 1.08 to the 6th minus 1 over 1.08 minus 1, and we get $11,003.89. Okay, the future value of an annuity. The future value of an annuity is the final sum. It's the total of all the deposits and the interest. An ordinary annuity is when payments are made at the end of each payment period. And that's really what we're going to use a lot of. The formula for the future value of an ordinary annuity is the future value, which is represented by S, equals R which is how much you're putting into the annuity each month, times 1 plus I, and remember, I is the annual interest divided by the number of compounding periods in a year, to the n is how many compounding periods, minus 1 over I. A shorthand way of writing this is S equals R times S angle N at I. That's just a shorthand notation, so if you see that, it means the same thing as our formula. On the formula sheet, you will have the full formula. A little technology tip. You may be delighted to learn that your TI 83 or 84 more than likely has a financial problem-solving application. If you go to the apps menu, most of them have a finance app that's preloaded. And if you select the finance app, the very first thing you see is TVM Solver. And the TVM Solver is what you can use to help you with these problems. Now keep in mind, I am still going to want to see the setup for these formulas on a test or quiz. So being able to use your calculator and app in your calculator does not mean that you don't have to be able to use the formulas. You need to be able to do both. The calculator is a great backup for you. Okay, so this kind of explains how to use it. First, what you do is you put in the known quantities. N is the number of payments. I% is the annual interest rate, and you will give it as a percent. Do not change it to a decimal. PV refers to present value. PMT is payment per period, so how much are you paying every month, or however often you pay. Now that's going to be entered as a negative amount because you are paying that out. P/Y is payments per year, and C/Y is number of compoundings per year. Often those are the same. At the bottom of the screen, you can set the payment to end, which would be an ordinary annuity, or begin, which we'll talk about later, would be a what's called an annuity due. We'll talk about that later. So for right now, it would be end that we're interested in. Okay, then what you need to do is you need to put the cursor on what you're missing, which would be FV for future value. Put it next to that, and then press solve. Solve is going to be alpha, and then enter. And when you do that, it will give you the future value of the account. Okay, and I do note there that the P/Y and the C/Y should always be the same for the problems in this text. Okay, moving on. Example. A rookie player in the National Football League just signed his first 7-year contract. To prepare for his future, he deposits $150,000 at the end of each year for the 7 years in an account paying 4.1% compounded annually. How much will he have on deposit after 7 years? Okay, we're going to use our formula. Pause this recording, see if you can do it, and then resume it to check your answer. Okay, it's an ordinary annuity because he is doing it at the end of each year. His payments are $150,000, which is represented by the letter R. N is 7 years, and the interest is 0.041. Okay, so we're going to use our formula. And it's being compounded annually, so when we do the 0.041, it would be over 1. So you see they kind of shortcutted it a little bit here. So you have $150,000 times 1.041, that's the 1 plus the interest to the 7th power minus 1 over 0.041. At the end of those 7 years, he is going to have $1,188,346.11 or 11 cents in his account. Let's try another example. We have Allison, who's a college professor, and she is contributing $950 a month to the CREF stock fund, and it tells you that's an investment vehicle that college and university employees have available. For the past 10 years, this fund has earned 4.25% compounded monthly. The first question is, how much did she earn over the last 10 years? Use your formula, pause the recording, try it, and resume the recording to check your answer. Okay, she has an ordinary annuity. R is $950. I is 0.0425 over 12. It's compounded monthly. And it's been 10 years, so 10 times 12 is 120, and that's going to be our N. Put all that into the future value formula, and you get $141,746.90. The question is that as of April 2013, the year-to-date return was 9.38% compounded monthly. If this rate were to continue and Allison continues to contribute $950 a month, how much would the account be worth at the end of the next 15 years? Okay, pause the recording, give this a try, and then resume the recording to check your answer. All right, we actually have to play this off of Part A. It says deal separately with the two parts of her account. The $950 that are going to be in the future and the $141,746.97 already in the account. The contributions form an ordinary annuities in Part A. So here's what we have. R is $950. She's still doing $950. The interest going forward from now for the next 15 years is going to be 0.0938 divided by 12. And N will be 12 times 15, which is 180. So what we're doing right now is we're figuring out just for what she starts contributing now until the end of the next 15 years at this new interest rate, what will she have? Put that in your formula and you see that at the end of the 15 years, just from now until then, she will have accumulated $372,068.65. However, we don't want to forget that she has already got over $141,000 from the first 10 years in the account. And it is now earning interest at 9.38% compounded monthly. So what we're going to do with this is we're going to go back to our formula from Section 2 and put that into our compound interest formula and find out what that's worth at the end of the next 15 years. So we have the principal, which is the amount that was already in there, $141,746.90, times 1 plus 0.0938, the new interest, over 12 to the 180 power, because that's how many compounding times we have between now and the end of 15 years. And we find that that amount will be $575,961.85. To get the total sum, you're going to add both of those together and find that after the 25-year period, she has $947,760.50. Okay, we have a couple more terms here, sinking funds and annuities due. A sinking fund is a fund that receives periodic payments. It can be an ordinary annuity. And an annuity due is an annuity in which payments are made at the beginning of each period instead of at the end. And the formula is going to be slightly different for these. The formula for annuities due is S, future value, equals R, that's your payment, times 1 plus I, again, that's interest divided by the number of compounding times in a year, to the N plus 1 power over I, and then you subtract R, you subtract one monthly payment from that. All right, example 4. A business sets up a sinking fund so that it will be able to pay off bonds it has issued when they mature. If it deposits $12,000 at the end of each quarter in an account that earns 5.2% interest compounded quarterly, how much will be in the sinking fund after 10 years? Now, this is an ordinary annuity because you are depositing at the end of each quarter, not month, quarter. Pause the recording, try the problem, and then resume the recording to check your answer. Okay, like we said, the sinking fund is an annuity. R is $12,000. It's depositing $12,000 at the end of each quarter, so that's the payment. The interest is 0.052 divided by 4 quarters. And N is 4 times 10, which is 40. You can see how we put all those numbers into our formula. And we find that at the end of 10 years, they have $624,369.81. So rounding it, $624,370. Okay, here's another example. A firm borrows $6 million to build a small factory. The bank requires it to set up a $200,000 sinking fund to replace the roof after 15 years. If the firm's deposits earn 6% interest compounded annually, find the payment it should make at the end of each year into the sinking fund. So again, payments are at the end. It's an ordinary annuity. Notice it's compounded annually. Pause the recording, try the problem, and then resume the recording to check your answer. Okay, again, we need $200,000. That's actually our future value. That's what we want to end up with at the end of 15 years. We don't know the payments yet, so R is going to be our variable. Putting all the other numbers in, our interest is 0.06, and that will be divided by 1 because it's annual compounding. It's 15 years, so N is 15. And then doing a little algebra, we discover that every quarter they need to deposit $8,593. Let's do another example. As an incentive for a valued employee to remain on the job, a company plans to offer her a $100,000 bonus payable when she retires in 20 years. If the company deposits $200 a month into a sinking fund, what interest rate must it earn with monthly compounding in order to guarantee that the fund will be worth $100,000 in 20 years? All right, same situation, different variable this time. Now we're looking for rate. Pause the recording, try the problem, and resume the recording to check your answer. Okay, the sinking fund is an annuity. R is 200. N is 12 times 20. Notice that the interest rate is compounding monthly. And the future value is 100,000. Interest is what we need. And it says if X is the annual interest rate, then the interest rate per month is I equals X over 12. So they're putting those values in. And what they're doing is they're compensating for the fact, remember, your interest is always divided by the number of compounding rates. Okay, so here we've got the problem set up with all the numbers in place. And it says this is kind of hard to solve algebraically, and it is. It's a tough one. So what we're going to do instead is we're going to use our graphing calculator like we've talked about before. You're going to go to y equals, and for y1 you're going to put in the equation. Be careful, watch those parentheses. For y2 you're going to put in 100,000, and you're going to see where they intersect. And when you do that, you should find that it's about 6.661%. You can also use your calculator, the financial application on there. But again, make sure you show how the problem is set up. Here's a little bit more about annuities due. We already said an annuity due is an annuity where payments are made at the beginning of each period. This little diagram is to kind of show you the difference in the interest earned between the two. Remember that with an ordinary annuity, because your payment's at the end, your very last payment is not going to earn any interest. With an annuity due, because you're paying at the beginning, every payment will earn interest. So for the annuity due, what you put in at the beginning of year 1 is going to earn interest for 3 years. What you put in at the beginning of year 2 will earn interest for 2 years, and at year 3 will earn interest for 1 year. Now, notice that this is very close to an ordinary annuity for 4 years, except you have an extra $100 or an extra payment in the ordinary annuity. So pretty much what we've got here is they've taken the formula for an ordinary annuity and they've just altered it slightly to accommodate the annuity due. So that's where our formula comes from. That's where, if you wondered why the minus R, it's because that extra payment is not in there. You can kind of see from the diagram. Okay. Now let's try an example. Payments of $500 are made at the beginning of each quarter for 7 years in an account paying 8% interest compounded quarterly. Find the future value of this annuity due. So use your formula, pause the recording to try it, resume the recording to check your answer. And here's our solution. N is going to be 28 because it's 7 years and it's going in quarterly. We're going to add 1 period because you do n plus 1, so that's going to bring it up to 29. And don't forget that our interest has got to be divided by 4. So you can see all the numbers have been put in place, and after 7 years, the balance on the account will be $18,896.12. All right, another example. Jay plans to have a fixed amount from his paycheck directly deposited into an account that pays 5.5% interest compounded monthly. He gets paid on the first day of each month, and he wants to accumulate $13,000 in the next 3.5 years. How much should he deposit each month? Okay, again, another annuity due problem. Pause the recording, give it a try, and then resume the recording to check your answer. Okay, this time we don't know R. We need to know the payments. What we do know is that he wants $13,000, which will be S. We know the interest is going to be 0.055 divided by 12, and there are 42 months in 3.5 years. So we're going to put all that information into our formula. Okay, and what they've done a little bit of algebra here. They have factored out the R, which is common to both, and then just put the numbers into their calculator, and we get R times 46.4103 is 13,000. Do division, and you find out that he needs to deposit $280.11 from every paycheck. And this is just a summary of our formulas. We had two. We had the formula for the future value of an ordinary annuity, and we also had the formula for the future value of an annuities due. Okay, here's some classwork problems. Give them a try. Pause the recording while you're trying them, and then resume the recording to check your answer. Again, pause the recording, try the problems, and resume the recording to check your answer.